This is Brennan.
And this is Tanner, and we did our project on time travel. So first, we will go over wormholes. Secondly, we will go over time machines. And lastly, we will go over our essential question.
So first off, what is a wormhole? So a wormhole is a hypothetical shortcut between 2 points in the universe. Wormholes have 2 entrances, 2 mouths, and they're connected by a tunnel through hyperspace. Now, hyperspace is a hypothetical 4th dimension in our universe where 3-dimensional space can be folded in order to create connections between 2 points. So, if you think about a piece of paper that you folded in half, then poked a hole in the middle of the paper that goes through both layers, and imagine that an ant wanted to walk from one side of the paper to the other, it would obviously be a lot faster to go through the hole in the middle than across and around the entire paper. Just like it would be much faster to get to a distant star, per se, through a wormhole in hyperspace than by traveling across the entire universe. In this hypothetical diagram of a wormhole, you can see the star Vega, which is a distance of 26 light years away from Earth. And if you were to try and cross the entire universe normally, it would take an unimaginable amount of time to get there. But instead, if we had a wormhole, the wormhole could just be a mere kilometers long, and you would obviously get there much faster by going through a wormhole in hyperspace.
The problem with wormholes. Wormholes were first discovered by Ludwig Flamm mathematically in 1916. And then in 1935, Einstein and physicist Nathan Rosen used the theory of general relativity to elaborate on the idea proposing the existence of bridges or wormholes through spacetime. These bridges connect 2 different points in spacetime, theoretically creating a shortcut that could reduce travel time and distance. The problem with using wormholes to travel in time or even space is that they are inherently unstable. When a particle enters a wormhole, it creates fluctuations that cause the structure to collapse in upon itself. There are theories that a wormhole could be held open by some form of negative energy, which represents a case where the energy density of space is actually negative. Additionally, wormholes have a short lifespan of about only a day, and once they disappear, they disappear forever with no ability to track it down, or no ability to track it down yet, at least.
So the solution to the problems presented previously with wormholes would be exotic material. An exotic material will hypothetically push the walls of the wormhole apart gravitationally while also defocusing light beams that pass through the wormhole. To do this, the exotic material must have a negative average energy density. Since Einstein's equation says that energy and mass are interchangeable, this means that the mass of the material must be negative. So instead of gravitationally attracting things, like as masses in our universe do, the gravitational field of exotic matter will repel the walls of the wormhole once threaded through the wormhole. However, once exotic material was discussed, the possibility of it being able to actually exist was very controversial among physicists. As it turns out, though, Stephen Hawking had already discovered exotic material in 1974 when he discovered that vacuum fluctuations near the horizon of a black hole are exotic. Now, these vacuum fluctuations can only be exotic in curved space-time, though, which is like wormholes, so that would work. So if, say, an infinitely advanced civilization wanted to construct a wormhole themselves, there would be a quantum strategy and a classical strategy of constructing a wormhole. For the quantum strategy, it would require the use of gravitational vacuum fluctuations, like previously discussed. It's theorized that gravitational vacuum fluctuations are everywhere around us, but they're so small that they've never actually been detected. So in a Planck Wheeler length, which is 1.62 times 10 to the negative 55 centimeters or smaller, these vacuum fluctuations have been theorized to boil and become quantum foam. And this is the same quantum foam that makes up the core of space-time singularities. And this quantum foam is everywhere and everything, so hypothetically, the advanced civilization could reach down into the quantum foam and have a very small chance to grab a wormhole, which they could then enlarge to classical size.
Now, the classical strategy of constructing a wormhole would be a completely smooth, singularity-free warping of twisting in spacetime. However, in order for this to be possible, time must also become twisted up while constructing is going on by time travel happening in both directions. The machinery used to construct the wormhole must also function as a time machine, carrying people and items from late moments of construction back to earlier moments. This classical strategy of constructing a wormhole was taken in skepticism by many physicists because many of them firmly believe that the laws of physics must forbid time machines, therefore preventing this way of construction.
Next is time machines. So how does time flow in wormholes? It was discovered that time is hooked up differently through the wormhole than in the external universe outside of it. So to explain this, let me give an example. Say one mouth of a wormhole is at rest in Mr. B's room, and the other end is traveling into space at close to the speed of light. As seen in the diagram, the wormhole is able to remain at a fixed length during the trip because, relative to hyperspace, the bottom part of our universe is sliding towards the right, while the wormhole and the top part of our universe, where Mr. B's room is located, remains at rest. So, from the external viewpoint of the wormhole, the mouths are getting farther apart from each other as the wormhole gets deeper into space. But if you're inside the wormhole, so from the internal viewpoint, the mouths are at rest with respect to each other. Here's how to theoretically make a time machine using a wormhole. So say you have a very short wormhole with one mouth in the living room and one mouth in a spacecraft outside on your front lawn. So you have two people. Person one stays at home with the mouth in the living room, and person two takes the other mouth in the spaceship on a very high-speed trip close to the speed of light out into the universe and back. So throughout the trip, person one and person two are holding hands. Person two departs at 9 a.m. on January 1st, 2022, as measured by both people and everyone else on Earth. Person two travels nearly the speed of light out into space for 6 hours as measured by person two. Person two turns around, travels back to Earth at the same speed for another 6 hours as measured by person two, which would make the trip 12 hours total. So person one is holding hands and watching person two through the wormhole this entire time. And so person one agrees, looking through the wormhole, that person two has arrived back on the front lawn at 9 p.m., 12 hours later, on January 1st, 2022. Person one can see person two, the house, and the lawn while looking into the wormhole. But person one looks out of the window into the yard, and person two and the spaceship are not there in the front yard. And at this time, if person one had a super telescope and looked out into space, they would see person two flying away from Earth. Now, 10 years later for person one, person two returns in the spaceship in the front yard on January 1st, 2032. When person one goes out to meet person two has only aged 12 hours, not 10 years like person one and the rest of the Earth have. And person two has their hand in the wormhole, holding hands with person one 10 years younger. And if person one were to go through this wormhole, they would meet themselves 10 years younger, and vice versa. If the 10 years younger person one wanted to go through the wormhole, they could meet themselves 10 years older. And now this wormhole has become a time machine. You can travel through the wormhole, and one direction takes you 10 years to the past, and the other direction takes you 10 years to the future. However, you're unable to travel back in time beyond 9 p.m. January 1st, 2022, because this is when the wormhole first became a time machine.
The trouble with time travel. First, there is the grandfather paradox. The grandfather paradox is a potential logical problem that would arise if a person were to travel to a past time. The name comes from the idea that if a person travels to a time before their grandfather had children and kills him, it would make their own birth impossible, and thus they never time traveled, so they were actually always born. So if time travel is possible, it somehow must avoid this contradiction. Next is Polzinski's paradox. Polzinski's paradox is similar to the grandfather paradox, where if you or an object travels into the past and prevents itself from time traveling, then the younger self would never time travel, thus it was never prevented by the object in the future from time traveling. So if time travel is indeed possible, it must also avoid a contradiction like this. A simple solution to this is that time travel to the past is impossible, through wormholes at least. Next is the bootstrap paradox. The bootstrap paradox is a theoretical paradox of time travel that occurs when an object or piece of information sent back in time becomes trapped within an infinite cause and effect loop in which the item no longer has a discernible point of origin. For example, if I travel back into the past and give my past self an object that my present self once had, it creates a time loop and the origin of the object is never known. Finally, the twin paradox. The twin paradox states that if one pair of twins makes a long journey and near the speed of light and returns, he or she will have aged less than the twin who remains behind. Time travel on time on Earth, appears to the moving twin as very, very slow, while for the twin on Earth, time is passing at just normal speed. The traveling twin cannot say that they are at rest because when they get back to Earth, the Earth is much older. Plus, in order to get back home, the traveling twin needs to slow down, turn around, and then speed back up to get back to Earth. These paradoxes are present issues with time travel that physicists are still trying to explain and figure out. This is an example of Polzinski's paradox, where the ball is traveling from time 3 minutes to time 3 minutes and 45 seconds. It's traveling into the right mouth of what seems to be a wormhole and exits the left mouth at a time of 3 minutes and 15 seconds before the ball was even entering the right mouth of the wormhole. This knocks the ball off its course and it ends up never entering the right mouth. And this is when the paradox comes into play. If it never enters the right mouth, then it never exits the left mouth, so it always enters the right mouth, which is why a contradiction like this cannot be possible if time travel were to exist, because it wouldn't make sense and it would just be a continuous loop of it entering and exiting the time loop, the wormhole, Now time for our essential question. Is it possible to travel to the past? First, we'll start off time travel to the future. Time travel to the future is relatively straightforward through the physics of Einstein's special theory of relativity that you can trade motion in space for motion in time. If you're standing perfectly still, you're moving through the dimension of time at the speed of light. As soon as you start moving through space, however, you slow down your rate of moving through time. In other words, the faster you move in space, the slower you move in time. Sergei K. Krikalev did something close to time traveling when he traveled on a space station going 17,700 miles per hour for 803 days, and he aged 1/48th of a second slower, or traveled 1/48th of a second into the future.
Traveling backwards in time is when it starts to get a little more complicated. When Einstein first came out with his theory of special relativity, it forbade time travel to the past. And then when he introduced his theory of general relativity, this lifted that, but there were still issues with it. His equations of general relativity had many different solutions to them, and these different solutions assign different qualities to the universe, with only some of them permitting time travel to the past. And for the ones that do permit it, time travel to the past must certainly involve wormholes. However, the laws of quantum mechanics might forbid wormholes, and if they don't, then they could still forbid the wormholes from being successfully converted into time machines. Another reason why time travel to the past might be forbidden is because of conservation of energy. So, say you have a wormhole that's been turned into a time machine that sends objects back 3 seconds in time to the exact same location, and you place the wormhole a few inches above a trampoline. You turn the wormhole on, and 1 second later, drop a weasel into the portal. It falls, appears 3 seconds earlier before the wormhole is turned on, and bounces off the trampoline to a point above the wormhole. 3 seconds later, there you are dropping the original weasel, and next to it is the weasel that time traveled and bounced. The wormhole turns on, and both weasels now fall through the portal. The cycle repeats itself automatically without human intervention. All you had to do was turn on the portal and drop the first weasel. 2 weasels become 4, which become 8, and so on. And that first one weasel would instantly become an infinite number of weasels. They would fill the entire universe, crush us to death, and just explode with all of the runaway energy. So some connections that can be made from time travel and wormholes to what we learned in class this year. First, there's Einstein's theory of special relativity, and in this theory is time dilation. And time dilation is all about frames of reference, the inertial frame of reference, the frame of reference that is moving relative to the frame of reference that is at rest, and the faster the relative velocity, the greater the time dilation will be. So these concepts connect back to our class. And then there's Einstein's theory of general relativity, and this looks at how gravity affects the fabric of space-time. And for his theory of general relativity, the laws of physics are the same for all non-accelerating observers, and the concept of acceleration and just the general laws of physics connect back to AP Physics 1. And then, like I previously just mentioned, how conservation of energy could forbid time travel, and this is also something that we learned this year.
And here are our works cited.